So chapter 7 finally starts doing something with the z-scores that we have been talking about, and that is setting up confidence intervals. So we're actually going to start doing some real statistics and not just probability and random z-scores. What a confidence interval does is kind of set up goalposts where you're going to say, I want so much of my data to be in between these two goalposts. Now you can pick any kind of percent of data that you want. Like you could say, I want it 80% confidence that what I'm going to have is in this zone, or 90%, or a 68.5%. But most of the time we use the same ones over and over again, and that is a 90%, a 95%, and a 99%. And honestly, we don't really use the 90% all that much either. And so we're going to kind of flip back and forth between these idea of probability in between the goalposts and the error that's floating around on the outside. So you see that a 90% confidence interval is basically a 10% error range where I'm willing to be this wrong on the sides. With chapter 7, the error in the tails, which I'm going to show you a picture of next, will always be the same size. So it'll be 5% on one side and 5% on the other side, with 90% in the middle. Most of the time we're talking about a 95%, which means 2.5 error on the right and 2.5 error on the left, or a 99, which would be a 0.5% left and a 0.5% right. So it looks something like this, where in my green zone is going to be my confidence interval that I want to be between this post and this post. And and there go the dogs. Then my error range will be out here, and you'll see that it was an alpha divided by 2, because if my alpha is 10, I want half on each side. So you'll see that little alpha divided by 2 symbol that pops up. So for a 95% confidence interval, that's why we were talking about those z-scores, like 95% of the area to the left, or in between this z-score and that z-score. I'll have this 95% with 2.5 out here and 2.5 out here. And we're really bad in stats about saying percents and writing decimals, or vice versa. You see we have a little bit of both here. In chapter 7, these z-scores will always be opposites, which in algebra means one's positive and one's negative. Now the goalposts will always be opposites, but we're only going to really, in our formula, we're only going to use the positive version. The good news is it's the same numbers over and over again, because we're always talking about a 95% or a 99%. So if I'm talking about a 95% confidence interval, where I have 2.5 error on the left and 2.5 error on the right, wedged in between is the 95%. And those two z-scores have to be a negative 1.96 and a positive 1.96. Now that doesn't mean that there's no other way to gather up 95% of the data, but to have the tails equal on both ends, that's the only way to do it. So it's kind of like the only way that you can add the same number and get 4 is 2 plus 2, right? But you can say 3 plus 1, 4 plus 0. There's other ways to get to 4, but the only way that they're equal is with that one pair of numbers, and that's the same thing here. We're going to have some new fun variables floating around. We're going to have this little p. That means population proportion. Eventually, we're going to have a big P also. P hat, that little like caret symbol that's floating around on top of him, is going to be the sample proportion. N is the number of sample values still. There's that Z alpha. And this capital E is going to be my margin of error. And we'll talk about that in a second. We're going to be working with our sample proportions, but then using that to set up a confidence interval for our population proportions for these P's. And remember, population proportion breaks the data into 2 groups. That doesn't mean that they can only be talked about 2 ways. It's just those are the 2 ways we're going to talk about it. So a lot of times what we use is odd numbers and even numbers, like you saw at the end of chapter 6, which is a little strange. Oh, do we do that in 6? We didn't do that in 6. But we'll do that now. We don't need to worry about that. So here's our range that we're going to be setting up. We're going to be talking about what's going on with the whole population in the middle, but those goalposts are going to be numbers relevant to the problem, and we're going to set that up using the p hat that we are given in the problem, plus or minus the error that we're going to have to find. Now, I'm going to do this by hand, and then I'm going to show you how to get your numbers on the calculator. I don't care how you do it, if you want to always do it by hand or you always want to do it on the calculator. Sometimes one way is a little bit easier than the other way. Your numbers may not be exactly the same, but I think if you never see it by hand, the stuff on the calculator is just magic, and then you have no idea where it came from. The calculator will not set it up looking like this, but like this third one down here, where it's going to almost look like a point on the plane, like if you were plotting X's and Y's. What you're actually going to do if you're finding by hand is the second one, where you're going to have a number, add some on, and subtract some off so that you can get the goalposts. This absolute value of p hat minus p is just a fancy way to say the second one. And anytime, if you're later on you do like a college algebra course or something like that, we often talk about that as a tolerance for when you're adding and subtracting at the same time. So this lovely formula can be found on that fold-out sheet, which is going to become your new best friend if it isn't already, because it has all the formulas on it. And this Z alpha 2 are going to be the magic numbers that we're going to use over and over again, which is coming up on another slide. It's going to say, all right, find this confidence interval. That's going to help you find this p hat. This Z alpha 2. Then you're going to take that number, multiply by the square root of the p hat and the q hat. Now remember, p is our probability of success. Q is then our probability of failure, so 1 minus p. And still the number of people in your study. Round to 3 significant digits, which on the next slide has this big long story of what a significant digit is. For us, it's not really a big deal. If you take chemistry or something like that, it becomes like this huge issue. For statistics, it's usually not ever a big deal because we're kind of dealing with numbers that are 3 to 4 digits and not super, super small or super big. Okay. Here are our happy critical values. You're going to want to write these down. Probably right on that fold-out sheet. A 90% confidence interval means you're going to use a Z alpha 2 of 1.645. 95% is a 1.96. 98% is a 2.33. 99 is a 2.575. Like I said, 90 and 98, not super popular, but they pop up now and again. 95 and 99 are the ones that we use a lot. You're going to want to write these down so you don't have to look them up 2 million times. So here is our story, a Pew Research Center poll of 1,501 people. The poll showed that 70% of the respondents said they believe in global warming. And so let's say that that is a success for us, that we want that people believe in global warming. And so p hat is 0.7. That's what we found out. We want to find the margin of error that corresponds with the 95% confidence interval. We want to find the proportion, population proportion, and then we're going to talk about what does that mean. So let's talk about what that means. If I can get this out of my way. All right, so here's my formula. To find the error amount, which is the first thing that I'm going to have to do, is I'm going to pull out this Z alpha. Well, you don't want to write? Why not? Oh. Now we'll do it. It doesn't want to write. We're going to find that Z alpha first. It's a 95%, so that's a 1.96. P hat was given to us. It's a 70%, so that's a 0.7, which means Q's got to be a 0.3 because that's our failure rate. Number of people in the study was 1,501. And then usually what I do is I kind of crunch this number backwards. I am going to take the number that's in my numerator, get that, divided by my n. This big long mess, which is always going to be somewhat of a mess, is underneath your radical. So now I want to take the square root of that. I hit second x squared. And then I'm going to hit second negative sign. That says take the last answer that I had and then take the square root of it. So second x squared and then second to the negative 1. Be on the lookout for these E's with these negative exponents after that. That means scientific notation. So this number is actually 0.0001399. That's my number that's underneath that this radical becomes. So it's 1.96 times this big chunk here. So times 1.96, there's my error. I usually go quite a few decimals out, probably more than I need to. And so my error is about a 0.023183, stop wherever. I mean, you can probably stop here at the 10,000s. So once I get that error range, I'm going to add it on to my p-hat to get my top end goalpost. I'm going to subtract it off of the p-hat and get my low end goalpost, and I get this range of 0.677 and 0.723. So what does this mean? It means that if I was going to repeat this over and over and over again in 95% of the polls, the error should be no more than 2.3 percentage points, which means if I do this over and over again, that every single time the p-hat that I get will fall in between this range. So if I do it 100 more times, 95 p-hats are going to be in that range. That's what it means to be 95% confident. So from here, what MyMathLab sometimes says is like, well, is it fair to say this, or is it fair to say that? And then this one says, well, is it fair to say that more than 50% of the population believe that we're in that we have global warming? Because the 50%, all this entire range is above 50%, then we can say yes. Had it been like, well, I can't change it, but if it was a 0.477 and it was just a little bit under, then I wouldn't be able to say it. But because the whole thing is above, then we're good. All right, so how do you do this in your calculator? In your calculator, this one will actually be a little bit trickier. The ones that are a little bit nicer to do by using the calculator is not when they give you the p-hat, but when they actually give you this many people said this, and they give you an actual person count. So I'll show you what I mean. In MyMathLab, number 9, and it's a little bit of a pain, it says a study of 420,020 cell phone users. They found 132 of them developed a cancer in the brain or nervous system. And they've been talking a lot about this lately. They said to keep their cell phone like 6 inches away from your head or something. Now, prior to this study, they found that the rate was this relatively small percentage of 0.03112. So they said, all right, construct a 90% confidence interval to find out what's going on now based on this study. And this one will be easier to do in the calculator because it doesn't say, oh, 70% of people you polled, or 68% or 59.3%. It says 132, a hard count. So when you see that, what I would do is grab your calculator. You want to hit Stat and go over to Test. And this is where we're going to live for Chapter 7 and 8. Chapter 7 is about intervals, and you can see my first one over here is a Z interval. You want to scroll down to 1 prop Z int. For me, it's A, and maybe a different number for you because I have kind of an older version of a calculator. 1 prop Z int, 1 proportion, Z because it's normally distributed, which means nothing to you right now, but it will in another video. Int for interval. Hit enter. This very small screen pops up. The X is the number of people that found or said or agreed with whatever it is that you were proposing. In this case, it's 132. 132 of my N, which was 420,020, had developed this rare brain or nervous system cancer. This C level is your confidence level, which can be changed. I'm kind of defaults to 95. We want it as 90. And then you're going to come in here and hit calculate, and it's going to give it to you. Done. Now here's the tricky part. See the little E's? We need to move these back 4 spots. So this is 0.00027. So 0.00027, right? If I take this decimal point and drag him back to the left 4 spots, this rounded 4 decimal places is 0.0003, and that's my low end. My high end is 0.00036, because drag this back 4 spots, jump over the 3, I need 3 more zeros. So rounded to 4 decimal places is 0.0004. Oh, as a percent. Now I got to change it to a percent, which means 2 spots to the right. And now my math lab is happy. So, do cell phone users appear to have a rate of cancer of brain or nervous system that's different than people who don't use it? And the answer is no, because the rate for the people who don't use cell phones is right in that range. Now, granted, it's pretty close to the bottom there. I mean, I wouldn't want to hear that I have only a 0.001% less or more chance of getting this rare form, but I cannot say that the cell phones are causing it, or because the people who don't use cell phones have the same rate. So does it appear that this is different? No, because it's included in the confidence interval. And that's all they want to know. Now, if I was going to do this one by hand, it becomes a little bit more of a pain, and I'll show you why, just real quick. What you would be looking for your p-hat is not the 132, but the 132 divided by this. And so you would have to find out what that number is. Now, notice right here that this p-hat is a 0.000314. When I find the p-hat by hand, it comes out to the same thing. But where I decide to round may throw off my numbers a whole lot when I go in and start doing this. So I could still use that and then move it over to the, oh no, I want the decimal. So I would have to work with this little tiny number, 0.000314, if I went that far. If I said, well, you know what, this is close enough for me, my numbers are going to be a tiny bit different. My math lab's been fairly forgiving as far as the ranges that they're willing to accept, but sometimes it could be a little picky. Sometimes they don't say, well, this is, find me an error, this is what I did. Sometimes they work backwards and they say, all right, I want to do this study and I only want my error range to be 2%, 3%, 1.8%. And a lot of times if you watch the news, you'll see plus or minus 3% for an error, and that's what they're talking about here. So if you say, well, I want to be able to conduct this study and I want it to have a specific error size. I don't want to have like a 10 or a 12% error, because then my survey is not worth anything. What I would have to do is, from this lovely formula that we had before, work backwards and find out how many people do I need to ask. Because you're going to know P and Q. You're going to know the confidence level that you want, but now you're saying, hey, I want a specific E value. So now the question is, how many people do I need to ask? And it comes way down to this formula down here, which is p hat times q hat times the square of the Z alpha 2, which is just that square, not everything, over E squared. So if you don't know a p hat, like you won't know in your Chapter 7 lab, we just assume a 50-50. So 0.5 times 0.5, that's where that 0.25 comes from. And these two formulas are also on that fold-out sheet. So eBay wants to determine the current percentage of U.S. adults who now use the internet. They want a 95% confidence interval. They want no more than 3 percentage points. And way back in 2006, we said 73% of adults use the internet. So let's first do this with how many people I would have to ask to have a 3% error now, using that same p-hat from 2006. And then we're going to do it again, pretending that we never had that survey. So if my p-hat's 73, that means Q's got to be 0.27. My alpha is a 0.05. So that means I want 95% confidence. I'm using my 1.96 again for my Z alpha 2. But now I want E to be 3 percentage points, so 0.03. Plug it all into this. That box should be a multiply. I don't know why it does that. So plug it into this. I have 1.96 in for that Z alpha. Only that is squared. Times 0.73 times 0.27. Get that numerator first, and then divide it by that 0.03 squared. And you get 841.3 people. Well, you can't have 0.3 of a person. And 841, even though it's super small error, right? I mean, it's only a third of a person, is technically not enough. So you always are going to have to go up to the next whole person. So we'll have to ask 842 people. If I'm going with a 0.73 for a p-hat, to have something that will give me a 95% confidence interval with a 3% error range. Now, it doesn't say what your range will be, but it just says you got to ask this many people. If I was going off of I had no idea what happened back in 2006, I would say 50-50. 50% of people use it, 50% of people don't. So 0.5 times 0.5 is a 0.25. This process remains the same. The only thing that changes is in here in these p-hats. Now you got to ask a whole lot more people, 1,068. Always round up to the whole person. You don't round the way you would arithmetically. In mathematics, this rounds to 1067. But for stats, we need another whole person. You can have extra. You can't be short. So think about your bill for your cell phone as $1,067.11. If you mail them 1,067, I promise you Verizon would be like, hey, you owe us 11 cents. So you have to make sure that you cover that also. I'm going to stop there for this part, and then we're going to talk about point estimates and how to find the mean confidence interval in the next one.